clustering, which I managed to do last time, and then I will show you the second part of my presentation, which is about more rigorous modeling and trying to achieve significance and stuff like this. So, as I said yesterday, clustering is somewhat similar in its aims and general outlook to the dimensionality reduction. So the idea is the same. You have these complex data characterized by many parameters. So you want to see if there is any structure in the data. You want to see if you can group, if you can find interesting groups in the data, and so on and so forth. So when I was younger, I liked to do clustering a lot. It was kind of popular then, and it's still popular now. But in recent years, I began to prefer dimensionality reduction. And I will try to show you in the next couple of minutes why this is so. Why I think that using dimensionality reduction techniques and visualizing is actually maybe preferable to just using clustering, or maybe even simply preferable to using clustering. So the main idea is the same. You have these points which live in this very complex space with many dimensions. You cannot visualize them. It's very hard to think of them. So what clustering algorithms do, they look at pairwise distances. Again, that's how different are points between themselves. And then they try either to separate all the points in n groups. You tell the algorithm, give me 3 groups in the best possible way. Or what they also try to do in other settings is that they try to connect all the points in a kind of tree thing. This is called hierarchical clustering, and I saw a couple of dendrograms in the posters, so I see that people use this a lot even here. So there are 2 basic kinds. Either you tell the algorithm I need 2 or 3 or several groups, and it tries to separate everything into this number of groups using some criteria, or you tell the algorithm, please give me the tree-like thing. So these are 2 approaches, and sometimes they use similar techniques, sometimes they use the same techniques, but sometimes also people do other stuff. There are more than 100 published algorithms of clustering, so there is no end to this, but these are 2 basic types. For instance, there is a thing called density-based clustering. What these guys try to do, these algorithms look at the space and we see a dense cloud of points here and another dense cloud of points here, and in between we see some points which are kind of alone. And unlike other algorithms, these algorithms say these points which are separated, they're just noise. They don't try to separate everything, divide everything into clusters. They also include noise points. So what is very important about clustering, and what many people who use clustering don't really understand, or at least they don't really account for. The problem is that when you use some clustering algorithms, all these algorithms have very strong assumptions about the data. So when they divide things into clusters, they do this based on some ideas. So for instance, we have these 2 clouds of points, right? So they form this interlocking structure. And ideally, we would like, probably by looking at these points, we would like to see them separated in this way, in the right way. So because there is a boundary between these 2 groups, and both groups are kind of coherent, and so on. But most clustering algorithms, what they do is they do stuff like this. Why? Because they assume that clusters form kinds of balls, right? So in this case, it's 2 dimensions, so balls are actually circles, and when 2 circles are in contact, the edge is more line-like. But generally, most of the algorithms which do this divide into several clusters, what they assume is that we have some kind of multi-dimensional balls. And if you look at Mark Donahue's slides from yesterday's lecture, he showed the several clusters. They all are precisely balls, because the algorithm he uses, it thinks about clusters as balls, which in many cases is just not true, because in this case the clusters aren't balls, they're like interlocking donuts or something like this. So, but the problem is that in this case we see these data and we say, okay, it's more or less evident that the right algorithm is preferable to the left algorithm because it suits the data better. But in this case, the data are dimensional, so there is no real need to do any kind of fancy processing. But in most cases, data are very much multidimensional, and you have no idea when you start analyzing analyzing the data, how they really look like, what they really look like, how we should analyze them. And then you can try different clustering algorithms, and sometimes they give very different results, and there is no way you can choose between them, because there is no real answer with clustering. Clustering is just poking at the data and see what pops up. So it's good when you use different clustering algorithms, and they all give you more or less the same results. This means that indeed there are very clearly separable groups in the data, and whatever way you choose to treat the data, it will give you the same results. In this case, it's more or less robust. You can say, okay, we're sure that indeed there are these clusters. But in this case, for instance, algorithms give you different results. And this happens quite a lot. So unfortunately, if you use clustering, you are never completely sure, you're never completely convinced that what you have as a result is not simply the truth, but maybe even some coherent picture, because you can use other algorithms, you can use a slightly different distance matrix, and everything falls apart. So clustering is very brittle, is not stable, and you should be very aware of it. And why I think that dimensionality reduction is in some way better, because it gives you this visual picture. And this visual picture may be messy, or it may be complicated, or it may be very clear. So you kind of see what's happening. With clustering, usually, because you have all this multidimensional data with many variables, you cannot visualize anything. You can just believe what you see or not. So, there are two basic approaches. Either the algorithms took the nearby points and collapse them together until we have one huge cluster, or they take all the points and then try to divide them into groups using some predefined algorithm. And there is a point of view in the literature that when you actually divide hierarchically things into groups starting from all the points at once, you achieve better results. But most of the algorithms are bottom-up rather than top-bottom, but it's good to know that there is another way of clusterizing, even when you do hierarchical clustering, which is when you want to produce trees. Okay, so I like to give examples from other fields. So for instance, when you can really use hierarchical clustering. So for instance, in genetics, people use all kinds of very complicated models to fit the genetic data to the tree. So they try to find the optimal tree which will fit the genetic data in some way. But all this algorithm, they need some initial input. So you need some initial tree which you then try to improve upon. And usually they use some hierarchical clustering algorithms. They feed the genetic data to this algorithm, and then they try to improve upon this result. So but basically it's the method of data summarization and exploration and so on and so forth. So for instance, if you remember, we had this transitivity data set. So I showed you I think I showed you this dimensionality reduction. No, I didn't show you dimensionality. So this is the way to look at the verbs from the point of view of how you derive transitive verbs from a transitive and vice versa. And we see that there are basically three kinds of verbs in the sample. So either we have the verb die or kill, which is clearly different. So the way you derive die from kill or vice versa is very different from how you derive transitive or intransitive versions from most other verbs. And most other verbs, they fall in these two groups. So we have things like improve, develop, dissolve, and rock on the one hand, and on the other hand we have things like destroy, break, connect, open. So one may say that one group are more like more transitive oriented verbs, so probably they are more often converted from transitive to intransitive when we make a derivation, and this group is the other way, but this needs to be checked. So this just gives you an overview of what we have in the data, and then again the interpretation is always up to you, and this is just a way to present some. Sometimes the picture is nice and you can say this shows us something, sometimes it doesn't. So we can do the same with languages, but we have more languages and it becomes very messy and hard to interpret. So for instance, we see the dialects of Japanese behave in the same way, which is nice, but also we see that English partners closely with Basque, Vietnamese, and Avar. And actually there is a story for this. I think there is a story, but basically, as far as transitivity is concerned, the derivation of transitive and intransitive forms of verbs, I would say that Eurasia is basically split in the central part, where we have all these qualitative languages, Turkic languages, Mongolic languages, and languages around them which have very strong qualitative patterns, and then we have the periphery. And the periphery, there is lots of suppletion and lability and stuff like this. So basically, English here is together with Basque on the one hand and Thai and Vietnamese on the other hand, because English and Basque are on the western periphery, and Vietnamese and Thai is on the eastern periphery. And then we have all these languages like Kyrgyz, Kazakh, Uzbek, Khakas, and Turkmen, which form this cluster over here. And I would guess that this is where causative patterns are very, very prominent. But again, this only gives you an overview, and then you need to go back to the data and analyze it to try to test some hypotheses which you can formulate. So this is basically for formulating hypotheses and then testing them based on data. But because people very often present trees like this as a kind of the end, the outcome. So we did some work, and this is the result. And this is never the result. This is just an overview of data. It doesn't give you any indication of whether you're right or wrong, and so on. So this is how I calculated the distances for the WATP data set, and you can use it to process the same file which is on the server, and this is how we do. And this is very easy in R. So if you have distances, or if you can use baked-in distances, that really this is all the code you need to compute the clusterization and then plot it. You just need the packaged cluster, which comes pre-built in R. You don't even need to install it. So then basically you use your distance matrix. I had my ones beforehand, but for some data it can be computed from the data themselves. And then you just use this function hclust, which basically computes a hierarchical clusterization using some method by default, which you can see from the help page. And then I use this as philo method just to have a circular dendrogram, because by default it gives you this dendrogram from top to bottom or from left to right, which is not as fancy looking as this circular one. That's why I use this package just to have the circular dendrogram. So this is really very, very easy. And I have all the fancy ways to color the different parts of the dendrograms. You can have one branch in green, one branch in yellow, and so on and so forth. There's lots of stuff on the web for these kinds of things. So this is what I showed yesterday, that you can try to separate your data, divide your data into several clusters, and then try to look at how they pattern geographically. And in this case, we're using not the hierarchical clustering, but the other type of clustering, when you give how many clusters you need. And this is much better viewed on your screens. And this is how I computed this clusterization, which is also very, very simple. So in this case, we have the data, which is, I think it's on the server, maybe under some other name. So you take this data, you delete all the metadata columns because I don't need them, and then we have this matrix, which is a binary. I think, yeah, it's a binary matrix because we have zeros and ones for different volumes. And then I just use the Manhattan distance metric, which I talked about yesterday. Again, use this function dist, which is included in the basic R. And then you use this, one of the methods for clustering things into a predefined number of clusters. It's called PAM. It's called partitioning around medoids, an improved version of partitioning around means. So this gives you this object, and this object basically contains information about which things fall into which cluster. So then you can just use this information to change the shapes of the points, and you can use colors. In this case, I use colors to change to denote the language group. So we have this. Eventually, we have this map with points of different shape depending on the cluster, and the points of different colors depending on the language group. So there is a legend here, so we know that, for instance, in the middle cluster there are languages of different groups, and this is also very convenient to do some kind of exploration. And the code, as you see, is very simple. It's all the code I need to produce this map. Okay, so that's it for dimensionality reduction and clustering. So if you have any questions, please ask them now. Okay, so if not, let's move to the second part of the course, which is about doing some more explicit modeling of the thing. So it's the file slides2 on the server, so you can open it on your screens as well. So it will be about trying to incorporate aerial information into the models. So you have models and you want to somehow account for the fact that languages are from different places, or that languages are close to each other, and so on and so forth. So there are several ways to do this, and I will show you two basic ones. And then I will talk for some time about how you can quantify this aspect of whether languages are neighbors or not, because this is often very important and people often try to do this, and I think that in many cases it is done in a suboptimal way, which can be Buddhism. So we begin with a technique which is very widely used and very well known in different parts of statistical analysis. It's called mental analysis. Basically it's derived from the surname of the guy who devised the test, or the mental test. So in this case, we are usually it's about basically computing correlations, but usually we compute correlations between two vectors. So we have, for instance, the vector of weights and the vector of heights, and we want to see if weights and heights of people are connected in a way. So there are very old and very well understood methods for computing correlations between vectors, like arrays of numbers. So in this case, what we're interested in is we want to compute the correlation between two matrices. And why we may want to do this is that you have some points, some data points like languages or trees or regions or people or anything, and then you have a way to measure how different these things are. So, for instance, if there are languages, we can count. We can try to. Let's say we have 3 languages, and then we may want to see if they have the same word order or different word order. So we have languages A, B, C here, and languages A, B, C here. So languages are always similar between themselves. So if we'll always have zeros on the diagonal. So let's say that language A and B have different word order. So it will be distance of 1. We will only have distances of 1 and 0. Languages A and C have the same word order, and as languages A and B have the same word order, languages have different word order, and languages A and C have the same word order, then transitively languages B and C will have different word order. So this is a very simple distance matrix, which is very primitive, and actually it may be fully specified by just one row, because it's enough to say that language A is different from B, but not different from C. Then we can derive everything from this. But very often, of course, these differences are more complex, because all pairs of languages will be different in some way, but usually these matrices are symmetric, because usually the difference is the same no matter whether you compare A to B or B to A. Okay, so this is one way of comparing these differences between the languages. And let's say that also we may be interested in whether these languages are from the same language family or not. So we say that the distance is 0 if they are from the same language family, and the distance is 1 if they are from different language families. So again, we have 3 languages, A, B, and C. Of course, we also have zeros here, and we also have zeros here. And then let's say that A and B are from different, but A and C are also from different language families, so something like this. And B and C are also from. We have each language is in its own language family. So now we're interested in whether these two things are correlated. So now we compute correlation between two matrices. And it's a bit tricky because we'll have to count the same things over and over again. And because we do this, we have a probability of false positive. And what Mantle basically did is he said, if we have two matrices and we want to compute a correlation between two matrices, then we should do some kind of permutation testing to make sure that we don't have a false positive. That's basically called Mantle test, and this is this is an example from a paper on ecology. This is what they do quite a lot. They say, let's see how distances in geography, I think in this case, correlate between distances in the biological makeup of some small pieces of land.
Excuse me, you said false positive, but what does it mean exactly?
False positive means that we have a hypothesis that something is because of something, that something is connected to something like this. And then we see that it's really the case. So let's say that like my mother is sure that some kinds of homeopathic therapies are effective for treating cold. I am sure that they're not true, but she says that they always help. So in this case, I think that the case when she takes a homeopathic medicine and it helps her is a false positive, because it's purely by chance that she felt better after taking this medicine. So in this case, we'll say, for instance, that it's true that...
May I take a picture?
Pardon?
May I take a cable and show a picture on it? It will be easier after you explain it.
Okay. But I think the cable is too short, so we should...
Anyway.
So false positive is when you assume that two things are connected and you observe that they are connected, but you observe this just because it happened by chance. In reality, there is no connection. So,
can you explain shortly why when we correlate matrices we have the risk of this false positive?
because
you say there is
You can show it.
oh, exactly. Yeah. So, what happened in this case? In the first case, we may assume that they made some tests, and then these tests kind of showed that this guy is pregnant. The result was usually connected with pregnancy. So, and they decided that he was pregnant. This is a false positive. So, why this may be harmful is because as we see that some things are connected inside this matrix. So, if you just take the standard correlation coefficient and you convert everything into a long vector and then do this, you will see that you count some things several times. You count same things over and over again, and that's you just need to. This is not something very tricky. It's just the particular calculation you need to perform in order to be sure that you are not overcounting things several times. So this is what Mantle did, and but basically what's interesting is that after the other guys came and said, okay, but let's say that we want to analyze whether there is a connection between two types of distances, given that there is also a third type of distance which may interfere with this. So this is called partial Mantle test. Partial Mantle test makes it possible to compute the correlation between two matrices, given that some other matrix also influences one of them or both of them. And there is a very famous example of using Mantle testing in linguistics. It's a paper written by Robert Ladd and Don Dedio. It was published, I think, in 2015. So it's about having terms, lexical terms in language, and its connection with genetics. So what they try to show is that there are two genetical markers. I don't remember exactly what kind of markers there are, so they use some kind of genetic data, and they call these two markers ASPMT and MCPHD. So the thing is that the higher is the incidence of both these markers in the population, then the fewer languages will have lexical terms. So this is kind of inverse correlation. So they show that there are like special mutations which impede gaining lexical tones in language. And this is how they report their results. And this is how people usually report their results when they do this kind of testing. So they see that there is a correlation with geography for tone is significant. But if you do this for one, so we have two markers. For one of them, it's so they use a correction, which I'll explain later. So they see there is a very small correlation, but it's and it's significant for one marker, it's significant for the other marker, and so on and so forth. So we can read to this more thoroughly later. So the idea is that when they take everything into account, the partial mental correlation between the tone and the presence of both markers is very significant. And why they need partial testing is because they control for geography. So when you control for geography, that languages which are very far away from each other, we see that they're less correlated in terms of having lexical tones. But still, when you control for this, you still see a significant correlation between the tone and the absence of these genetic traits. And then they have this absolutely unrealistically, I would say, looking model. They say if you have low frequencies of both SPMD and MCPHD, you only have tonal languages. If you have high frequency of MCPHD and low frequency of SPMD, you have both tonal and non-tonal languages. And if you have both high frequencies of both markers, you have exclusively non-tonal languages. So this looks very, very suggestive, and I would say happens not very often that we have results of this kind, but the most important thing is that they report all these kinds of mental testing between distance matrices. So what kind of distance matrices they use? They have a genetic distance matrix, they have a geographical distance matrix, and they have a distance matrix which basically counts number of tones. They just put ones for tonal languages and zeros for non-tonal languages. So if the languages both have tones, the difference is 0. If one of them has tones, the other doesn't have tones, the distance is 1 is like this. So they have these three types of matrices, and then they compute the correlation. So we can do some mental testing ourselves. So in this case, I use phonological data. So I took constant inventories from my database and from Foible. And then I computed the Jacquard distances between inventories, which I talked about yesterday. And also we have phylogenetic distances. So I say that if languages are from the same language group, the distance is 0. If they are from the same family but from different groups, the distance is 1. And if they are from different families, the distance is 2. And also we can look at whether they are not in contact, but where they are geographically neighbors. And we'll see later how this being neighbors is defined in my model. So if the languages are neighbors, then neighbor distances are zeros. If not, neighbor distances are ones. And finally, we can just use geographic distances, basically traveling distances. So we can take all these kinds of matrices and then do some mental analysis. So this is how the data look like initially. So we have language pairs, and for each language pair we show whether they are neighbors, whether they are from the same family and from the same language group. And I computed separately the Jacquard distance between the inventories. So I use Python just to have pre-baked distance matrices. And then to have some initial idea about how this plays out, I used TSNE. So I took these distances, phonemic distances, Jacquard distances, and dimensionality reduced everything into 2D. And we see that basically languages from the same families, they tend to cluster together. So we see some family here, some family here, but for instance this yellow family is all over the place. So clearly, being from the same family does not guarantee that the languages will be close to each other phonologically. And then we can do all kinds of correlation analysis. So in this case, we start with just computing the correlation between the phonemic distance and the travel distance, geodesic distance. We see that all the correlations are rather high. So we have three kinds of p-values. So basically, this is the one we're most interested in. So we see that there is a significant correlation, but also we see a significant correlation with languages being neighbors or not being neighbors. So now we begin to combine this analysis. So now let's look at whether it's important if languages are neighbors if we take into account raw distances between them. And actually it still is significant. We still see the p-value of 1,000, and this actually continues even if we take into account both geodesic distances and phylogenetic distances. Still the dependence on whether languages are neighbors is significant. So that's how we can do this, and you can choose your own distances. You can take syntactic distances, morphological distances, lexical distances. You can have genetic data. You can have all kinds of data. For instance, if you know that some languages were in contact in the past, you can use the number of years or centuries of contact as your distance. So if languages were never in contact, then they will have huge distance. If languages were in contact for 100 years, they will have a very small distance, and so on and so forth. So all kinds of things can be quantified for this kind of analysis.
Excellent. And what about the table with language pairs? Is it true that it's not a full table? Because not all the combinations are...
No, these are just the first several rows. So I think I have around... So it's languages of Eurasia, so it's about 500 and something languages, so we have...
But we have to have for all pairs for all languages.
Yeah, but
Pairs
this...
for all languages.
Yeah, but this is... You need to have this kind of distance matrix. So, like for three languages, we have this not 6, but 3 points, because we don't need diagonal. But yeah, you need to have full distance matrices for everything.
But they are present in a table.
So yeah, here we have everything. Yeah, basically here we can convert everything from the table to the distance matrices. And if you look at the
but when we use R, we have to have the table with or matrix.
So yeah, if you use these algorithms like this one, you need distance matrices.
Oh.
So here many things are called dist. So we have neighbor dist and fielder dist and so on and so forth. So you prepare the distance matrices in some way. Yeah, you can do it in many kinds of ways. For some things they're easy to compute. Like for instance, you remember on the previous slides I showed you this clusterization which was prepared based on this transitivity data. So there I used the dist function. So this dist function from the basic R installation, it computes a distance matrix. So we can have a matrix with languages with some variables, like for instance presence or absence of some consonant, or some presence or absence of some word, and so on and so forth. And then you just feed this matrix with data into the distance function, and it returns you the distance matrix. And then you use the distance matrix here.
And these are different objects in R, different tables.
Yeah, but in this case they need to be different tables, but tables of the same type and of the same size. Okay, and also mental test gives you an interesting type of plot, which is called Correlogram. It only shows the dependence between two matrices. So how it can be read is that we see that if languages are, let's say, so here we have geographical distance on the x-axis and the correlation on the y-axis. And what it shows you is that if the distance between languages is very small, then the phonological inventories will be very highly correlated. If the distance becomes larger, then the distances will be negatively correlated, which means that as you go further and further apart, inventories become more and more different. And then you have these white points, which means that after around 8,000 kilometers, there is really no connection. So if languages are 10,000 kilometers apart from each other, they do not influence each other in any way. So they're basically randomly, there is no connection between them. And this makes it, yeah, so you can, for instance, if you want, for instance, to define some areas, some predefined areas, and you want to think about how big this area should be, what you can do is you can do this type of mental analysis, and then you will see when the correlation becomes insignificant, and then you will say, okay, so my area should not be bigger, for instance, than 6,000 kilometers from west to east, because if it's bigger, then there will be no connection whatsoever between the endpoints. So this is how you do the analysis between matrices. And another popular way of doing this is basically constructing linear models and making the distance between things a predictive variable. So this is a very long, very basic way of doing things, and so there is some particular discussion I want to draw attention to. It's about whether there is a significant decrease in the average number of phonemes in the phonemic complexity of language as languages become further and further away from Africa. So the idea of Atkinson, who published this paper in Science in 2011, was that as people migrated from Africa all over the world, as they got further and further away from Africa, they kind of lost segments. So the inventories became smaller and smaller and smaller and smaller. Do you know the best example of this? Basically, the Austronesian guys, because we know that the Proto-Austronesian inventory was quite normal, because they had around 30 consonants, I think. But as they moved from the Proto-homeland on Taiwan further and further away into the Pacific, they gradually lost segments along the way, and people just see. So here they lost L, here they lost glottal stop, and so on. And then the easternmost inventories are the most simple ones. So what Atkinson basically says is that the same happened all over the world. As people were moving further and further away from Africa, the inventories were slowly becoming smaller and smaller, and he tried to prove this by constructing a model where he tried to predict the complexity of an inventory based on its language family, population size, and the most important predictor for Atkinson was that the distance from Africa. So how far the people should have walked to reach this point. So then a couple of guys.
Because I didn't figure out, even with the help of the internet, whether random test could have the negative values of correlation. Because what I see from the formula is something like n multiplied by n minus 1 divided by 2.
Yeah, but this is how we compute the p-value. The correlation itself, it's about computing the p-values. I think he takes the basic correlation coefficient and then he does some clever thing with p-values. And p-values are always positive.
No, what I was interested in is no, it's not like
Yeah, I think it's possible. It's just very, very unrealistic as things become further apart in one dimension, they become closer to each other in another dimension.
yeah, it's possible for cities you have something negative correlation.
Theoretically, this is possible, but
Cities you have big amount of.
we can try this with this. Okay, so then a couple of people came and said, okay, so your approach is interesting, but your model is bad. So you didn't take into account all the possible scenarios, so then it's not significant. And then there is this very, very recent paper, which is available online. It's called Modeling Linguistic Variables with Regression Models, and then it has types of models in the name. It's very recent. I think it's created maybe a month ago, which is very interesting. And if you're interested in computational statistical linguistics, I very much very much encourage you to basically read all three, but the last one is maybe the most informative just from a methodological point of view. So they all used the same basic technique. So do you know how linear regression works? So in linear regression, what we do is we have some response variable and we try to predict it by taking other things into account. So basically, so what we say is that we have some variable, and we can predict the average value of this variable using some data. So what these guys did is they take this basic model and they used what's called mixed effects linear models. Have you heard about mixed effects linear models? So in basic linear regression, let's say you have two men and women, and you want to predict average height of a person. Let's say you want to predict an average height of a person. But you know that in the population you are studying, men have different heights than women. Let's say men are shorter than women on average. So then, if you predict an average height for a person, you will predict an average height of an average person, which will be something between a man and a woman, and it will be meaningless, right? So you need to somehow account for this situation. And in classical modeling and basic linear regression, what you do is you say, okay, we have another variable, which will be 0 if a person is a man, and 1 if a person is a woman. And then we will predict the average height of a man, and then we will add something, some quantity, which we will compute separately, to convert this average height to a woman. So basically what you will have two different models. You will have a model for a man and a model for a woman. And you will have these two slopes. So let's say we model the height based on weight. So we have weight on the x-axis, and we say that on average, as people become more and more heavy, they become taller. But they become taller with this. They become taller with the same speed. Let's say we can also model speed differently. But what's interesting here is that we have two different models for men and women. So. And this approach is not very interesting in other situations, because, for instance, let's say you have pupils from different schools, and you see that pupils from different schools have different marks. They do less or more well on some kinds of tests because schools are different. What you want to do is you want to abstract away from this thing, because you have many schools, and it's impossible to have 1,000 models for 1,000 schools if you have a national survey. So what you want to do is you say, okay, let's take all this data into account, and then we abstract away from different groups. And this technique of abstracting away from different groups in your data is called mixed effects. Because you say we have a random effect as school, or a random effect as gender. In this case, we have a random effect of language family. Because let's say that languages become, phonemic inventories become less or more complex as you go further and further away from Africa. But everybody knows that different language families have different numbers of phonemes on average. So we should take this into account. And that's why we use mixed effect linear models. And here we have a picture, I think from the original paper by Atkinson, which shows that if you look at different families, for some families, the phonemic complexity decreases very sharply as you go further and further away from Africa. For other families, the phonemic complexity decreases but slowly. But for some other families, like these two guys, actually, as you go further away from Africa, the phonemic diversity increases, not decreases. And then you need to have a model which will take all this data into account. So basically, the discussion between Atkinson and his opponents was that Atkinson said, I used these mixed effects properly, and I proved that as you go further and further away from Africa, phonemic diversity decreases. And these guys said, no, we didn't use it properly. You forgot to account for the fact that different families have different slopes. They only took into account the different families have different baselines, different average values, and they say that you should also take into account average slopes, average speed, with which this happens, and this is why your results are insignificant. And they use basically the same techniques and the same, maybe in the same software. So now everybody does this mixed effects models using this package LME4 for R. It's very good, and there are very detailed introductions into how you use this and how you construct your models. So if you use basic linear regression in R, this is just an extension of this, so it's very user-friendly and very nice actually. But then this guy, Christophe Coupet, he came and said, see, even if you take all these things into account, if you do all this proper mixed effects modeling, still there are some assumptions about the data which your models do not satisfy. So the most important thing is about linear modeling, or basically any kind of statistical modeling, is that you assume that when you predict something, you predict it with some confidence. You have data points. Let's say I try to predict some. Say I try to predict the number of segments in some language family, and I say that it's on average 20. So what this means in practice? In practice, this means that when I predicted something, it is okay for me if some languages in this family have 22 segments, some have 18, maybe some has 23, maybe one has 40, and one has 5. But the idea is that on average, it's like this. And the noise is kind of, as they say, normally distributed around this mean. So we have the mean, which we predicted, and the errors should be distributed in this fashion around this mean. So this is a very skewed normal distribution. It should be like this. So this assumption is called the normality of residuals. So basically it says that the errors that you make in prediction should behave in some particular way. And we have a way of testing for this, and this is one of the ways of testing for the errors. And we see that here the errors should all fall around this line. And you see with these errors sharply deviate from the line. So, and if this happens, then this means that the assumptions on which our modeling are based are not satisfied. And this basically means that all that we report is bollocks. It can be a false positive, it can be anything, it's just meaningless. So, but the problem is that it happens quite often, and people say that, you know, these mixed effects models, they are, they say, robust to the normality of residuals, and there is actually no clear way to say when the deviation is too extreme. So for instance, for Atkinson and for these guys, they're not fools, they know that the normals, the residuals are distributed in a kind of tricky way, but they say, okay, we can live with that. And this guy comes and said, no, we can't. You should be more strict, you should be more rigorous in your modeling. So how do you do this? You either try to do funny stuff with your data, you do all kinds of transformations which make your data look more normal, and some people do this, but when you do transformations, you make it harder to actually understand what your model is modeling. So this is covered in most of these textbooks, and I will not delve into this. But what he says, let's just try to add more complex models. And what can we do when we try other things? We can try other types of distributions. So usually we say that the results, that the values which we are predicting should be distributed like this. But we can make another assumptions about the response variables, about the thing we're trying to predict. And there are several distributions we can check. We can also try to add some clever things to make our predictions look not like this, but maybe like this, or something, and so on. It's called Additive Models. So I'm really going very quickly over this. There are many things which can be analyzed in more detail. But also what we can do is we can say, okay, so our errors may be differently distributed based on different families. So this means in practice that, for instance, we can predict both the average number of phonemes in Indo-European languages and the average number of phonemes in Sino-Tibetan languages. And in the basic models, we assume that the average error will be the same in the European family and in Sino-Tibetan family. We will make the same amount of errors. But if we have more complex models, then we can take into account the fact that there is more diversity in Sino-Tibetan family than in the Indo-European family. That's what this boils down to when we say that we model not only location, but also the scale and shape of the distribution. So basically we say errors are different in different families, and you need more interesting techniques for that. So, and then he does all this, and he constructs a series of models, and he actually very nicely he says, I use that and that R package to construct this model, so you can just repeat all his steps after him. And then what he comes eventually to is that this line where they see that all the errors fall on these straight lines, so now the errors are normally distributed, all the assumptions are satisfied, we're happy. And basically he says that Atkinson was right, that if you take into account all these things, that indeed if you go further and further away from Africa, then the phonemic diversity is smaller. But the problem is that he has to use more complex models. So this is the general trade-off which we always see when we try to do the analysis. So either we can take a very simple model which will show something in a very clear way, like for instance, as you grow older, you tend to lose 2% of your hair every year. Like, this is a very simple model which is very understandable. But on the other hand, if we propose this kind of model, then we will have these non-normality of residuals and all kinds of statistical inconsistencies which are troubling. So what we can do is we can take these all very complex models which will have very nice properties, but then we ask, and what actually are these models telling us? So if I grow older, how much hair I'm losing every year? And people say, oh, it's really hard to say. You see that there is a general connection between age and the amount of hair you have, but the real relationship is complex. So this is the choice we have to make. Either we have very simple relationships, statistical kind of non-normalities, or we have very complex relationships, which is very hard to talk about, but everything is very good mathematically. So as I said, he corroborates Atkinson's result, and also we see that there is some very slight connection between the phonemic diversity and the linguistic density in the area, so maybe it points to the role of phoneme borrowing, but the effects are actually pretty slight. And in general, we see that all these models he talks about, they're available as R packages. So this is available to everybody. We can read his paper, we can download the stuff, we can read the documents and try to reproduce and play with this. So never be shy about this. Okay, so now we'll go on to quantifying neighborliness. So do you have questions about the previous part? Okay, so what I will be talking about now is very simple. Is how we know if the languages are neighbors. The answer is very simple. Just look at the map and you'll see if they're neighbors or not. But the problem is that we have, let's say, 500 languages or 2,000 languages, and we have that many language pairs, which is very many. And then it's impossible just to have this huge table of languages, of language pairs, and we just cannot do it manually. So what we want to do is we want to somehow automatically see if languages are neighbors on the map based on their coordinates. And we usually do this, and why are we interested in this? We're interested in this because if we use geographical distance as a predictive variable, it's on one hand it's very understandable. Oh, okay, of course, we just take into account how far languages are from each other. On the other hand, it's rather weird. So why does it matter how far from each other? If you look into the literature language context, all these classical books by Matras and people like this, do they really think about how far languages are from each other? Like, never. People don't think about this when they think about language content. What they think about is whether languages are neighbors. Are they in contact in some way? Or at least can they be in contact? This is understandable. Raw distances, much less understandable. So that's why we wanted to know if languages are in contact. And how we do this, we use neighbor graphs. Which can be computed based on the data. And I say that there are two basic ways of creating neighbor graphs. The usual one and the good one. So the usual one goes like this. So you have languages on the map, lots of them, and you want to know which languages are in contact. So you start with a particular language, and you draw a circle around this language of some radius. Usually people use 1,000 kilometers, which is kind of a lot. And then they say, okay, so this language doesn't fall inside the circle, so this is not a neighbor. But everybody else, they are all neighbors of this language we are interested in. So then you just connect them in your matrix or in your graph or anywhere. So, and then you repeat this procedure for all the languages. So for instance, you take this language, you draw a circle around this language, and these guys already accounted for, and then you add this edge, and this edge, and this edge, and this edge, and so on. So this is how it's often done. So it's very easy to do. It's a very straightforward program. Everybody who knows how to program can do this in a couple of minutes. So, but why this may be not the best way to do this?
I consider only one location for each language.
Yeah.
So Russian is 1,000 kilometers around Moscow.
Well, yeah.
Yeah, but in the end we will see such a map.
Yeah. Big languages are an issue. But big languages, if you want to do something clever with big languages, as there is only a couple of them, you can later go back to the distance matrix and modify the values yourself. So if you know that language is in contact with Nikh in the Far East, you just look for this Russian Nikh cell and you put 1 there. So this is not really an issue because it can be practically modified. So, but why this particular technique may be not really advantageous?
I don't know, but it doesn't really take into account also the counter contact between languages. I mean, languages can be in contact even if geographically they are not spoken in an area which is close to each other. Right?
Yeah, but they usually use 1,000 kilometers, so it's rare that languages are in contact while being more than 1,000
Right, but
kilometers.
if you're speaking a Creole or a Pidgin in an area that is not close to the motherland where the colonizer language is spoken, right?
Yeah, but this case is, I would say this case is rather, I don't know, so you're saying that if you're speaking a Pidgin, then you're somehow, you kind of were in contact with the mother, like, yeah, it's okay, but this is a problem of large distances, right? It's the same, so we can add large distances for large languages because only English and French and Spanish have this kind of relationships. But I'm talking about small languages. Why is this kind of
But
relationships?
not special will be problem. So for instance, we have neighbors, but they don't have no contact because of some religious problem or something like this.
We don't care about this.
Or maybe there's like a mountain between them and then...
Yeah, this is, what we can do actually, yeah, that's right. We can, it's hard to account for natural boundaries in this case, in this way.
But also for cultural phenomena. I mean, if you speak Arabic because you're a Muslim in an area that is not close to Arab countries,
Usually there is some degree of language conflict.
yeah, there is, but you cannot take it out.
Yeah, but I'm saying that,
So it's the same problem with Russian.
okay, so
It's solvable in the same way. as
Right, but
Russian.
it's more correlated to another set of phenomena.
but let's just look at more simple things. So let's say we have very small languages.
It's not that name.
So
So
what is a small language?
small language is just language which is spoken, like say the diameter of the linguistic community is like 10 kilometers, which is very often.
But does it mean much? I mean, sorry, I just being too critical, but I mean, do we count small language in area, not the number of speakers? Because
Yeah, now at the moment we're talking about small, geographically small languages, but they tend to be small in number of speakers as well.
But I mean, do they? Because we have in Russia we have, I don't know, Chukchi language, so you can't really say what area do they cover. I can say, I mean, not Chukchi exactly, but some of nomadic people, they cover a lot, but they are not.
Yeah, but so this is an issue which comes up a lot.
And also in Asia we have, I don't know, in Bangladesh, for example, where the density is very high, I do think that we have a lot of languages that people who live there in these conditions where you have to live in a villages, but you are full of people. So I mean, maybe I mean to.
Yeah, but I would say that the problem of nomadic people is not very extreme actually, because most languages, because we have thousands and thousands of languages, we can come up with several dozen examples of languages which do not have stable location and so on. But most languages actually are quite stable geographically and have small areas. So statistically, we can just see that this is noise. All these complex examples which are interesting and so on, they are basically noise. But what is really problematic with this approach, from my point of view, maybe you won't agree with me, is that when we're talking about small languages, which are in the majority, we can have languages which are basically densely packed like this. And this is true about Cameroon and New Guinea and many places in Amazonia and so on and so forth. And if we take this 1,000 kilometer radius, we'll have this language in contact with this language, which is clearly not true, because they never are in contact. They only are in contact if they are at all, they are in contact for these intermediaries. So what we should do, in my opinion, is that we should take into account the local density of languages. So if the languages are sparse, if we have Russian here and maybe Tatar here, then yeah, there will be a long edge. But if the languages are very densely packed, then we should take into account the fact that they are densely packed and not just blindly take all these 1,000 kilometer long edges.
There's a really nice point by Don, because 1,000 kilometers on the Earth, on the land, is really huge amount of space, and nobody will travel a lot to this. But in the sea, it's much easier, and it's not the distance. So for instance, you have a lot of...
Yeah, and that's the issue of having fixed edge lengths, which is also bad, because you can do drawing in both directions. Like, so what I'm saying is that we should adapt the length of edges between languages based on local density. And there is a way to do this. It's one of the basic geometric algorithms called delinear triangulation, which is basically you connect languages. You divide everything into triangles, and you make a triangle only in the case if you draw a circle around this triangle, there will be no other points inside the circle. So we see here that all these three guys, they are connected by edges, because if you draw a circle around these three guys, no other points in this set fall inside this triangle, so, inside this circle. So this is one of the ways of doing this, and it's very practical, and I think the results are more or less neat, so I like it. Maybe there are other algorithms, but as I was always satisfied with this one, I didn't really...
You need three guys anyhow.
Pardon?
You need three guys anyhow. You need three villages or boys.
Yeah.
Yeah, but you have something Russian Tatar, it will again.
Yeah, but then again, go back to the matrix and add one for Russian and Tatar. Okay, so here there is another implication that our coordinates are in this latitude-longitude shape. So we have longitudes ranging from negative 179 to positive 179, and the same thing with different numbers for latitudes. So and we have this boundary where it jumps from negative 179 to positive 179, which is not that good. And also there is this issue of projection, so we don't know distances very well. So what I propose is that instead of using coordinates, we just use points on the Earth as 3D coordinates. So we can do delinear triangulation in 3D. So this is not Earth, evidently, but it illustrates the basic thing, the basic principle, which is now you divide everything into simplices, basically into pyramids with four 1, 2, 3, 4 points. And what's interesting is that this triangulation, it always computes the envelope, the surface which encompasses all the points. So we see this green surface here, it's the kind of surface which envelopes all the points, and we see that it's composed of triangles. So what I propose to do for these situations is that you take the languages, which always lie on a sphere, on a kind of sphere, because Earth is basically spherical. You compute this triangulation, and you have all these triangles by themselves, which just fall out of this procedure. And it's very easy to do, and so you compute this envelope, which is called convex hull, and there are routines, there are functions for this in Python and in R, and then you extract triangles from these convex hulls. Basically, you extract these things, and you say this is an edge, so these guys are neighbors, and so on and so forth. And then you just say, okay, so if the edge is too long, if it's like 8,000 kilometers, we can drop it. And And then you can do all kinds of clever things. You can say, if an edge crosses a mountain ridge, which is also a kind of straight line, delete it. If the edge is too long for the continent, delete it. If the edge is too long even for the ocean, delete on the ocean. So you have full control over how you construct the resulting graph. So we have all the edges initially, and then you just delete everything you don't need, and then I come back and add stuff, Russian and English and Arabic and Spanish and all these languages which are in contact with many languages. So this is the code in Python. Again, it's rather straightforward. You convert the latitude and magnitude into x, y, and z, and then you compute this envelope, which is called qhull. This is the function for you, and then you extract the triangles, and then you add them. In this case, I simply add them to the graph if the edges are not longer than 1,000 kilometers, and this is the result. Exactly. Okay. So this is how it looks like. What it looks like in Eurasia. So this is Russian. Some edges are clearly missing. We need some edges connecting Russian to basically all these guys around it. But for the numerical majority of languages, which are in Eurasia situated here, in Southeast Asia, in the Himalaya, and in India, we basically see the picture which we would expect to see, which is nice, and I think this is a better way to construct, because it has fewer spurious edges than just using this 1,000 kilometer thing. So, yeah, so I just show this table once again by showing neighbors. In this case, 1 means that there is an edge somewhere here connecting these two languages. So now we can do all kinds of stuff with this data, in addition to mental analysis. So for instance, we can say, okay, so now we have groups of languages. We have languages which are from the same family, languages which are from the same family and the same group, languages which are from, and languages which are neighbors or not neighbors. So we have 6, in my data we have all this, we have 6 different kinds of language pairs. So in this case we see that languages are not neighbors, but they are from the same family. No, these are languages which are not neighbors, not from the same family, not from the same group, of course. These are languages which are not from the same family, but are from the, not from the same group, but from the same family. And these are languages which are not neighbors, from the same family, from the same group. So this is everything, so this is all the same thing all over again. Languages which are neighbors, but are not from the same family. Languages which are neighbors and are from the same family but not from the same group, and finally the language pairs which are neighbors from the same family and from the same group. So now we have all these 6 different groups of languages, and now we may want to estimate how are they different from each other. For instance, is it important if you are neighbors if you are from the same group, or is it important if you are neighbors if you are from the same family but not from the same group, and so on. So here I use a technique called bootstrapping to compute confidence intervals. I will not explain it now in detail because we don't have time, but basically we do some kind of repeated sampling, we compute distances, and then we look for the average values. So, and if they're different, in this case they're very much different from each other, so this is an average value for one group, this is an average distance for another group, and we see that they're very, very different. So then we can plot these differences, the confidence intervals for these differences, and very nicely we see that all the groups are significantly different from each other. So if we take languages which are neighbors from the same family, from the same group, the average phonological difference between them will be very small. The average difference for languages which are so neighbors, same family, same group, neighbors, same family, different group, not neighbors, same family, same group, not neighbors, same family, different group, not neighbors, and this was the previous one, and this is not neighbors, different families. So we see that all groups are different from each other. And what does it tell us? It tells us that, that all things are basically important. For phonological distances, it's important that you are from a different family or from the same family. Also it shows us that it's important are the languages, if the languages are neighbors or not, even they are from the same family and from the same group, because these confidence intervals do not overlap. So this is a kind of proven result. It's we did a test. We had hypothesis, and we had very nice. This is the code which I'll skip, and this is basically the result. So we kind of have a kind of hierarchy of how language pairs are different from each other if they are from the same group family and so on. So this is how it can be done. So this is basically all an illustration of using neighborness as a predictor. Okay. So yeah. So I have another section, but I think we can just stop now because the main ideas have already been presented, and it's basically another illustration of the same basic principle that you can use being neighbors as a predictor. So basically, what I do here is that I say, let's try to predict some feature of a language based on the features of its neighbor languages, and then we use the same graph to choose the neighbors. So, questions?
In the case of the second way to do it, when say considering density, you're considering an amount of neighbors in the world. So to say, instead of a radius which depends on a density, you just say the first 3 neighbors or something like that, or?
Well, I use this Delaume technique, which is kind of a proxy for all the things you're talking about. So the exact answer will be I take 3 guys such that if you draw a circle around them, it doesn't include any other guys. So this is the exact answer. This is the measure of neighborness, the measure of density that I use, and it's completely adaptable. So if we have 3 guys which are around some desert, for instance, then and nobody is inside this desert, then if you draw a circle around them, nobody will be inside the circle. So I will have these long edges.
Okay.
So it kind of does all the necessary things by itself.
But what about those you have are villages where you have data. But what if the real region where the language is spoken is not exactly this polygon?
That's called noise.
Sorry?
That's called noise.
Okay, but
Statistical noise.
okay, but can you play around with that? So move them. So if the real, so if this language is not going to be the first one, but with the second in the plot, because the way you choose the dots is slightly different. So you can try it like add random noise and repeat it many times, or take more than one circle of 3.
So you propose that I randomly commute the dots, and then what? I take the kind of average neighbor graph.
Yeah, or you just add it. So you're saying that every language can only be neighbor with 2 other languages, something like that?
No, it depends on typology. Sometimes languages have more neighbors. So if we look at the picture, come on. So, for instance, this guy is neighbors with 4 languages. This guy is also neighbors with 4 languages. This guy is neighbors with 1, 2, 3, 4, 5, 6 languages. So no, it depends on typology. You can have these dense clusters with many.
Why are not neighbors
But these guys, because more than 1,000 kilometers. So yeah, I can add this edge and I can add this edge maybe if I want to. But
why don't you use all settlements?
But this is just a crying shame database because there are no varieties of Arabic for some parts of the
There are
language.
not data set where we have all settlements where we use the same technique. The result will be much clearer.
Yeah, but I'll never have all the settlements for all the languages in Eurasia. This is a technique to deal with too much data. It's not about the optimal way of doing research on some particular area. If you know settlement patterns,
it's better to work with this on a particular area, not good for the whole Eurasia style.
yeah, but the thing is that I don't know a better way to deal with large areas, with lots of languages in many places, for which I will never have the settlement patterns. I don't know about settlements in this area, or in this part of the world and so on. Only the guy who wrote a grammar provides a single, let's say, it says, language is spoken here, I get it. Okay, language is spoken here, I believe you. And then we have the noise, which is, yeah, maybe if we move some stuff around, then we'll have different ages. But I would say that there is no better way to do this at the moment. Maybe?
But would this be a technique that is useful also in the opposite case? So I guess more or less what you were saying, if you have the list of languages spoken in each settlement and you want to create a pattern like this for a very small area, would you recommend using this technique? Or is
So, yeah, but it will be quite straightforward because what you do, so here we have just one language associated with one point. So basically the algorithm says draw an edge here, and as we have one language here and one language here, we connect two languages. But if we know that there are two languages spoken here and two languages spoken here, we can just connect them all in this case. So it will be just a slight adjustment.
See, I just wanted to know whether this system you would recommend it when we are working with a huge amount of data rather than with a set.
But if you have
Small scale.
if you have several dozen languages,
Okay.
then maybe it's realistic to just, for each, like you have this 10 by 10 table or 20 by 20 table, which is huge, but still, for each pair of languages, you can say, okay, these guys are in contact, I know this, these guys are not in contact, and so on. So yeah, this is a kind of a bag of shortcuts. We can make a shortcut here, we can make a shortcut here, and then boom, we have the whole Eurasia covered. Big
You're
deal.
actually going off the geography from this because you're actually from this kind of models you calculate modify the language in North Russia. How many consonants will I have or something like this?
Why? I can still use basic coordinates as the predictors. I can say that I know, for instance, that Northern Russian varieties are in contact with some Karelian things and Peps and so on and so forth, and also I can incorporate the raw coordinates, and then I will be able to take into account both these. So this is just the way of adding more predictors, which I think are important because I think that languages being neighbors are one of the most important predictors for many kinds of linguistic variables, and people don't do this in principled fashion. That's why I'm talking so much about neighbor graphs and stuff. Okay, it's 7 p.m.
Sure question. In
Yeah.
slide number 10, in this plot. So
Slide number 10 or page number 10?
Uh,
There is different system.
slide number 10, page number 14.
Page number 15. Hmm?
Yes. You say that this correlation decreases with distance but starts increasing again?
No.
Say,
So I would say this is just, again, random noise. So
okay, but you say from 10,000 is random noise or from 6,000 there's noise and it's like a
no,
composition of noise and...
that's just an example. I would say that from 6,000 on is just
okay. Yeah.
not really. But the problem with correlograms is that they're notoriously hard to interpret. I read several sources trying to explain what basically this means, and they all, it's very complicated. You know what this thing says. It's really complicated. It's really
You know there's something, but...
but basically I use this to just see the inflection point, the point where the distance becomes meaningless.
Okay, you say yes, because meaningless, it becomes like the opposite effect.
This is weird actually. So the system says that this is significant, but still, you see, this correlation it kind of goes up, but it's still negative. So we still see the negative correlation.
Yeah. I would say it's like you have this, I don't know, hyperbola or whatever, this shape, plus random noise, and the effect of the random noise is increasing, and that's why you see the
It's kind of
positive.
it's depressing the strength of the correlation.
Exactly. Yeah.
So real random noise is here when it's become positive again. This is just absolutely unbelievable. So so this is the flipping point basically, which is interesting. But everything else.
Up to 6,000 it makes sense.
And there are several papers which basically say that 6,000 kilometers is where all kinds of spatial dependencies and morphosyntax and in anything can just disappear. So that's what makes it interesting that Atkinson's model of distance from Africa still holds. He has much more than. So maybe he found this particular thing which really kind of works even on very long distance.
Yeah, but that's one variable. It looks at full inventories.
Yeah, and it has this index of complexity of what it means.
Also, distance from Africa doesn't mean distance of migration, right? I mean, people who came to North America and then went to migrated to South America,
Yeah,
they're
they-
approaching Africa again.
No, they don't.
Or you count the
Yeah,
trajectory.
they have these two, even three, I think, what they call bottleneck points or congestion points. So basically, the idea is that when you count distance, if you are in South America, you must pass through Beringia and through basically through Sinai Peninsula. So it will be like this. So yeah, they have a way of taking into account the migration. Okay, so thank you for the time.
Thank you.
Can someone turn on the light, please? Because I will switch this off and become very dark.